Okay, so for the second part of 6.1 here, just to take off from where we left off in class, we're doing acidic salts part 2. So just a reminder, go back here. So acidic salts is when you have a positive ion that essentially will hydrolyze with water and produce a hydronium ion, right? So actually this is the conjugate of a weak base. So the second type of salt that will create an acidic solution is if you have an anion of a strong monoprotic acid with a small highly charged metal cation. Okay, so highly charged in this case, we're talking about +3 and up. So what ends up happening is, for example, aluminum. So when we have aluminum ion, so let's say we had, let me erase that. So let's say we had aluminum nitrate as our salt, right? So when this breaks up into aluminum ions, so the nitrate we know would have no impact, the aluminum creates a hydrated cation. So aluminum will not just stay by itself. What ends up happening is it forms a structure with 6 other water molecules to create this aluminum water complex. And this in itself will essentially behave as a weak acid. And actually, if you look at this on our orange charts, we have the Ka values listed, and there's quite a few of them on there. So for example, there is a chromium complex, there is a, let me get the list here. Yeah, aluminum complex, there's an iron +3 complex, just to give you an example. Right? So it's the same deal, right? So iron +3, when it's in solution, will actually form this hydrated, oh my gosh, I labeled it H3O, a hydrated complex with the 6 waters, okay? So aluminum, as far as I can see on your chart, the ones that are most common are aluminum, chromium 3, and iron 3. Okay, so here's some example problems. So we have iron 3 nitrate, so which really means we have nitrate and we have iron +3, which we know will make that iron water complex. Calculate the pH of a 6 mole per liter iron nitrate solution. So we know that we're going to have iron hexa aqueo iron ion with water, and this is going to behave like an acid, which will make hydronium Fe. This will give us 5 waters now and a hydroxide, and this guy's going to be +2. So if we have the, right, if we were to create an ice table, we have this as being 6 mole per liter, right, 6 minus X. So if we want the pH, we still want the concentration of hydronium at equilibrium, right? So plus X, this is X and X. So because we have this Ka value, it's really going to be X squared, and then 6.0 minus X. The Ka value here is 6.0 times 10 to the -3. And then, of course, we check the 100 rule. Let me just grab my calculator. Okay, so in checking the 100 rule, so just to remember how we do that, you take your initial concentration, you divide by your Ka. Funny enough, this actually works out to be exactly 1,000. So we are going to take that, get rid of that X, and essentially it's going to be our Ka is equal to X squared over 6. So if we isolate out for X here, we get 0.1897 approximately. And then, of course, for the pH, we do the negative log of that. And then for sig figs for pH, we go to the sig figs here. We have 2, so that means we need 2 decimal places. So this is 0.7, oh my gosh, 0.77, it's 0.72. Okay, next. What concentration of aluminum bromide? So remember, so this breaks up into aluminum plus 3 and bromine. We know bromine is the conjugate of a strong acid, so that's not having an impact. But we want to know the concentration that will produce a pH of 3.25. Okay, so we know eventually, of course, the Ka value here is going to be for our aluminum water complex. So let's get our hydronium concentration, which we know, of course, is equal to our equilibrium value. So that's going to be 10 to the negative 3.25. And that gives us 5.623 times 10 to the negative 4 moles per liter. So our Ka here is, of course, always our concentration squared over, in this case I'm using X as my initial because that's what I'm trying to solve for, right? We know what the difference is. And if the Ka value from our orange chart for our aluminum, our hexaaqueo aluminum ion is 1.4 times 10 to the negative 5. Right, so once we isolate out for that, our initial concentration is 0.02315, etc., moles per liter, but it's 2 sig figs because it's 2 decimal points. So 0.023 moles per liter is our initial concentration. All right, so unlike the other alkaline earth cations, a hydrated beryllium ion will hydrolyze by donating protons to water. So here's another water complex ion, but of course they're giving us the Ka value here because this is not in our orange sheet. So we want to calculate the pH, and we have an initial concentration. Beryllium, we already know, will have an impact, and then iodine won't because it's the conjugate of a strong acid, right? So we have, let's just set this up. We know our Ka is going to be X squared over 0.400 moles per liter minus X. Our Ka value is here, so just double check the 100 rule. So 0.4 divided by 3.2 times 10 to the negative 7. So that gives us, 1.25 million. So that's definitely gone. So we're going to have here 3.2 times 10 to the negative 7 is equal to X squared over 0.4. So our X in this case works out to be, let's see, 3.2 times 10 to the negative 7 times 0.4, and if we take the square root of that, 3.5777 times 10 to the negative 4. And then, of course, for pH, we're going to do the negative log of that, which will give us negative log answer. So we need 2, actually Ka is a constant. So for sig figs, we'd be looking at this concentration, which is 3. So we need 3 decimal points, which would be 3.446 for the pH. All right, so let's take a look at what happens if you have, so we haven't seen this yet. So we talked about what makes something an acid, what makes something a base. But now we're going to look at, well, what happens if both ions have an impact? So what if the positive ion, so the cation and the anion, are both creating solutions that are changing the pH? Okay, so what you would have to do is really compare the magnitude or the size of the Ka and Kb. So if it's acidic, your Ka should be larger. If it's basic, your Kb will be larger. And of course, it will be approximately neutral if the Ka and Kb are close to being the same. Okay, so for example, here you have NH4, which we know is the conjugate of a weak base. And we have fluorine, which is the conjugate of a weak acid. So both of these will have an impact. So what you would do here is you would have to analyze both reactions and compare the values. So I'll show you what I mean here. Okay, so because NH4 is behaving like an acid, we need to look up the Ka value for NH4, right? So the Ka value for NH4, we can just simply look that one up, right? So this is 5.6 times 10 to the negative 10. But our fluorine is behaving like a base, right? So it is doing the accepting to become HF and hydroxide. So our fluorine ions are behaving like a base. So we would have to compare the Kb of the fluorine. So Kb we don't have. We'd have to solve for Kb by doing Kw over the Ka. So the Ka here, remember it has to be the conjugate. So if we want the Kb for fluorine, we have to look up the Ka for HF. So that's going to be 1.0 times 10 to the negative 14 over, for HF, we have 3.5 times 10 to the negative 4. So that gives us a Kb, 1.0 times 10 to the negative 14 divided by 3.5 times 10 to the negative 4. Okay, so that gives us a Kb value of 2.86 times 10 to the negative 11. So now you're just comparing them. Let me write this up here. 2.86 times 10 to the negative 11. So because the Ka is larger than the Kb, that means that when we have ammonium fluoride that's in water, it would create an acidic solution. Okay, so really both processes are happening. You're going to have both equilibriums. But remember, the larger the K value, the more product you have. So the equilibrium that has the larger K value is indicating which one we have more ions of. So we have more hydronium than we do hydroxide. Okay, so taking a look here, determine if a solution of, so this is ammonium acetate, will be acidic, basic, or neutral, and include the hydrolysis reactions that occur. Can you predict the approximate pH of this solution? Okay, so actually we already looked up the Ka for NH4. We can just look this up when we did already. So this value here for our NH4, where did it go now on my paper? Oh, 5.6 times 10 to the negative 10, right? So we want the Kb for our acetate. So that means we're going to be doing Kw over the Ka for acetic acid, right? So this is 1.0 times 10 to the negative 14. Acetic acid here is, where am I looking? Oh my goodness, I am blind. 1.8 times 10 to the negative 5 to solve for our Kb. Okay, and approximately, 5.6 times 10 to the negative 10. So actually, because they're pretty much the same, when we want to approximate this pH, the pH is going to be approximately 7 because they're incredibly close to each other. Okay, so we will continue the rest of this in the next part.